In this screencast, we are going to talk about elimination mechanisms and reactions, and we're specifically going to talk about E2 reactions. So there are two mechanisms of elimination, E2 and E1, just like there were two mechanisms of substitution, SN2 and SN1, that we learned about in the previous chapter. You're going to be able to draw a lot of similarities between them, which is really nice and helpful. So for example, the E2 mechanism, right, is a bimolecular elimination. And the E1 mechanism is a unimolecular elimination. Right? Now, the E2 and E1 mechanisms differ in the timing of bond cleavage and bond formation, very similarly to what we saw in the SN2 and SN1 mechanisms. Now, E2 and SN2 reactions have some features in common, and E1 and SN1 mechanisms do as well. So, without any further ado, let's jump into the E2 mechanism. So, when we talk about this particular reaction, what we're going to see, if we were to look, for example, at this molecule reacting with a base here, okay? So remember, it's going to attack a proton, so that's why we call it a base, okay? So what we do is we identify the alpha and beta carbons first. So the alpha carbon has the bromine on it, that's the halogen, and the beta carbon is right here next to it. And what we're going to see is that these electrons come and they grab a proton. When they grab a proton, these electrons hop down to make a double bond, and then these electrons go onto the bromine. We form a new bond, specifically a new pi bond, and water, and then bromine here. Now, when we look at this, this is the most common mechanism for dehydrohalogenation. It exhibits second order kinetics, just like SN2 did. And so that means when we look at the rate law, it is going to be based on the alkyl halide, or the concentration of the alkyl halide and the concentration of the base. So if you were to write it for this specific reaction, you would say, look, the rate equals the rate constant times CH3, and there are 3 of those. And that's the alkyl halide times the concentration of OH minus. Now, I want you to notice this is a concerted reaction, which means all the bonds are broken and formed in a single step. Now, there are close parallels between the E2, SN2 mechanisms, and so the identity of the base, the leaving group, and the solvent all affect the rate. And we're going to look at each of those through this screencast. So let's first jump into the identity of the base. So E2 reactions are generally run with strong, negatively charged bases like hydroxide or a deprotonated alcohol, which has those negative chars on it. Now, the base appears in the rate equation. So the rate of the E2 reaction increases, right, as the strength of the base increases. Okay. On this slide, I have two very strong sterically hindered nitrogen bases. These have quite long IUPAC names, so most people refer to them as the abbreviations here of DBN and DBU. And so you will see those being used in E2 mechanisms sometimes, and so it's just helpful to realize, hey, look, those are strong bases that are used. Let's then now look at the leaving group. So when we look at the leaving group, because the bond to the leaving group is partially broken in the transition state, the better the leaving group, the faster the E2 reaction. So the better the leaving group, the faster the E2 reaction. We also find that polar aprotic solvents increase the rate of E2 reactions as well. Okay, so let's look at, right, the structure of the alkyl halide. So SN2 and E2 mechanisms differ on how the alkyl halide structure affects the reaction rate. And that's a big deal. That's one of the ways we're going to be able to tell these two reactions apart. And so what we find is that as the number of R groups on the carbon with the leaving group increases, the rate of the E2 reaction also increases. So let's talk about why we see this. And the best way to do this is to talk about the transition state that's shown here with the reaction. So when we look at the transition state shown here, we're seeing the transition state where this base is going to come in and steal that proton. And so what's happening here is, right, this bond is forming, this bond is breaking because it's moving over here to form, right? And then that bond is breaking. So you have a partial negative here and a partial negative there. And so because the double bond is partially formed, that increases the stability of the double bond with the alkyl substituent stabilizing the transition state. Okay, so in the transition state, the double bond is partially formed. Now, this increases the stability of the double bond with those alkyl substituents stabilizing the transition state. And we stabilize the transition state, we lower that activation energy, right? And that in turn increases the rate of the reaction. Now, increasing the number of R groups, right, on the carbon with the leaving group forms more highly substituted, more stable alkenes in an E2 reaction. Okay, so look, if you have a primary alkyl halide here, you are going to get a mono-substituted product, and that's less stable than if you have a tertiary alkyl halide and you get a di-substituted product. Because remember, in the previous screencast, we said, hey, look, right? When you look at your double bonds here, you need to figure out how many R groups are around the double bond, because the more R groups you have, the more stable that alkene is. And so because this is more stable, this reaction occurs faster. So increasing the number of R groups on the carbon with the leaving group forms a more highly substituted and therefore more stable alkene in E2 reactions. So let's look at a summary of everything that we've kind of talked about so far. So here's the E2 reaction mechanism summary. When we talk about the kinetics, these are second order. It's a one-step mechanism. The more substituted halides react faster, where we see tertiary reacting faster than secondary, reacting faster than primary. They're favored by strong bases. The better the leaving group, the faster the reaction. So we saw that as the size of the leaving group increased, right? That would become a faster reaction. That's a better leaving group. And then the solvent, it's favored by polar aprotic solvents. So what happens when alkyl halides have two or more different beta carbons? Well, when that happens, more than one alkene product can be formed. Okay, so let's look at this guy. Okay, we have this little happy molecule here, and there is our alkyl halide, and so we can say, hey, look, that means that that little carbon right in there, I didn't like that alpha, so let me try again. That little carbon right in there is my alpha carbon. And I have two kinds of betas here. I have a CH3 here, and then I have a CH2 and a CH2 here. And so which one should I choose, right? And if you choose to remove the proton from the first beta, the beta one here, you would get a double bond that's tri-substituted. It has 1, 2, 3 R groups. If you remove it from the beta 2 here, you get a double bond that is just di-substituted here. That is a minor product. Now, the Zaitsev rule is what we follow for this. And what that states is that the major product in beta elimination has the more substituted double bond, right? That means it's the more stable alkene. Now, when we look at this reaction where we have a major product here and a minor product here, right? This is an example of a regioselective reaction. Now, a regioselective a reaction, well, let me say this. A reaction is regioselective when it yields predominantly or exclusively one constitutional isomer when more than one is possible. So a regioselective reaction will yield predominantly or exclusively one constitutional isomer when more than one is possible. Okay, so we can say then that the E2 reaction here is regioselective. Now, what we also find is that a reaction can be stereoselective when it forms predominantly or exclusively one stereoisomer when two or more are possible, right? So this is an example of an E2 reaction that is stereoselective because it will form both the cis and trans isomers, but it will form more of the trans isomer, which remember we said that was more stable, so that's the major product, than the cis isomer. So when we talk about a stereoselective reaction, right, this forms predominantly or exclusively one stereoisomer when two or more are possible. So that ends our discussion of E2 reactions, and in the next screencast we are going to look at E1 reactions. As always, if you have any questions, please feel free to stop by my office.